moving right along, in this video we're going to learn how to take the derivative of the quotient of two functions. You need a new rule called the quotient rule. Okay, so do you guys remember what a quotient is? Kind of like in the case of rational functions being the quotient of two polynomials. A quotient is a ratio of two different functions. So let's say h of x is the quotient of f of x and g of x, which is to say the new function h of x is formed by taking f of x and dividing it by g of x. Sometimes I'll call this one the top function, sometimes I'll call this one the bottom function. Alright, now what if we want to take the derivative of that? How about we just take the derivative of f and divide it by the derivative of g? So the derivative will be the quotient of the derivatives. No, not going to happen. Remember the video on product rule that you might have just watched? If we had a product, the derivative of the product was not the product of the derivatives. If we have a quotient of two functions, the derivative of that quotient is not the quotient of the two individual derivatives. That would be a lot easier than what it actually is equal to. And in this case, if you want to take the derivative of the quotient, it's equal to this mess right here. Alright, now let's go over it. Notice that this itself is a ratio of two things. On the numerator, we have the derivative of f times g of x without taking its derivative. Minus, note the minus here, which is different than the product rule that has a plus, minus the derivative of g times leaving the function f of x alone. Then we're going to take that entire difference on the top and divide it by the quantity g of x, the bottom function, squared. So we have to take the entire bottom function, you see I've surrounded in outer parentheses, and we're going to square that. That's the rule. Okay, so you see it again in the other notation here. The d dx of h of x is df dx times g of x minus dg dx times f of x, and then you divide that by the quantity g of x squared. Alright, so let's do a simple example to start us out. And just like with the product rule, I'm going to start us with one that we could consider two ways. Like for example, let's say we have 7x minus 1 on the top and we have x cubed on the bottom. If there ever is two ways that you could do it, I would recommend trying out both just to make sure that you've entirely got it right. And the reason I'm saying that there are two ways that I could do this is because I could actually break up this fraction. Now you're not going to be able to break up every single general quotient here, but in this case, because I just have the one term x cubed on the bottom, I could break this up into two terms. Alright, so why don't you check your pre-calculus skills right now, and before I write it down, pause the video, and how would I break this up? What am I trying to say here? So what I want to do is take the 7x and divide that by x cubed, so that would just be 7 divided by x squared. See how one of the x's canceled? And then I'll break that difference up, minus 1 over x cubed, or if you like it, which I do in terms of negative exponents, that's this function. I really like it better in terms of its negative exponents here, because remember the power rule can be applied to all real number exponents, in this case minus 2, minus 3. That's just fine. I'm going to do the power rule the same way I ever would. And it's a little bit harder to see that I can and should use the power rule when I've written it as this fraction. Actually, oftentimes, people will take a term like this, let's say 7 over x squared, and they will say, uh-oh, that's a fraction, gotta go to the quotient rule. It's not always necessarily true, and this is an example where you can do a little shortcut. 7 over x squared is 7 times x to the minus 2. Now I don't need the quotient rule because in order to take the h prime, just using this statement for h of x, 7 times minus 2 is minus 14. X to the minus 2 minus another one, so minus 3. Okay? Minus times minus 3 is plus 3. X to the minus 3 minus 1 more. Remember, when you're in the negative powers, the actual number seems to go up because minus 4 is minus 3 minus another 1. Okay? So that's why it looks a little different. But I can see through simplification and rewriting in terms of negative powers, I can see what the derivative of this function is already. So that's really going to be great to use for a first exercise on the quotient rule, because the quotient rule is quite a doozy, isn't it? I find that maybe it helps if I write the two functions of interest in color here, and then you can kind of see where each term went. And so let's try to keep track of it that way. Okay, because there's a lot of different things going on. So taking the derivative, I've written the top function f of x in red and the bottom function g of x in blue. So just keep track of it like this. I wrote the g of x like this and the f of x in red. Try to color code it there. Okay, and now let's just follow along with the instructions. And by the way, if I was going to test you on stuff like this, I would provide you with this equation, okay? So this is something I wouldn't expect you to memorize so much as just be able to apply at will. All right, so just follow the recipe. Here's the recipe. F prime. So I'm going to take the red function and take its derivative. What's the derivative of the red function? 7. That's right, that's a linear function, so its derivative is the same as its slope. Times g of x, and it says don't do anything to the g of x, you just leave it right alone. All right? And then I'm going to take a g prime. What's the derivative of the blue function? 3x squared, right? And then I'm going to leave the red function alone. That was the top function. I'll just leave that alone. And finally, what do I have to divide the whole entire thing by? Not the derivative of g, but just g itself, quantity squared. So now I have to take the x cubed and do a square to it. And do you remember what the rule is for that? The next thing I'm going to ask you to do is simplify this so I can confirm that it's the same thing as this answer that I got right here using the other way. So this is a really, really good chance for you to test whether you're ready to move on in calculus. There's a lot of pre-calculus skills right here in the simplification of this. Pause the video and simplify this function for me, and when you're done and you rewrite it in terms of its negative powers, you should get that underlined function, okay? I highly recommend that you test yourself right now to see if you're there. Okay, so I'm going to do it with you now, so I'll just go to black now, where I'm going to combine like terms. This top is 7x cubed. Minus, looks like we have a 21x cubed there. And then we have a minus 3 times a minus 1, so plus 3x squared. And then I'm done with the top, okay? Now when you're doing the top, because we have a negative, a subtraction here, we didn't have that in the product rule, but in the quotient rule, you got to be so careful with your parentheses whenever you have a negative, because that negative has to factor through. Okay, so make sure you enclose everything like I did in parentheses and factor through any negative signs you may have to deal with. That's where I got the plus 3. And then this part, I was wondering if you guys got this. X cubed to the 2 is x to the 5, 6, 7, 8. It's multiplication, okay? If you have x to the a to the b, that's x to the a times b. All right, that's a strong pre-calculus skill that we need you to have. So this is going to be 3 times 2, which is 6. So I put the 6 right there. Okay, but that's not the simplified form because there's a lot of other things that I can do. Like here's 7x cubed, and there's minus 21x cubed, right? So that would be altogether a minus 14x cubed. Okay, and then over here we have the 3x squared, and that's all over x to the 6. Is it the same as that I got before? There's one more thing that I need to do, which is going to be to take each one of these terms and individually divide them by x6. Just like I'm doing here. And here's another place that you're going to need to know your pre-calculus skills. This is x to the 3 divided by x to the 6. So that means I have 3 more on the bottom than I do on the top. And that's why I say that this first term is equal to minus 14x to the minus 3. I don't want you to think that's a quotient. Okay, and see how I got the minus 3? That's 3 minus 6, minus 3. On here we have a plus 3. And then what kind of x do we have? Let's see. X to the 2, and then x to the 6 on the bottom. 6 is 4 more than 2, but it's on the bottom. So if I'm going to put it on the top, x to the minus 4, and these two are the same thing. Yay! And that's what we should get if we have 2 methods. It is so satisfying to just do both methods and see that you didn't make any mistakes, you're on the right track, and you know how to use the rule. Okay? Let's go on to another example, and in this example, I am going to give you a function that you cannot do in the other way. You're not necessarily always going to be able to divide out by the denominator, and that's actually the main reason we would want to use the quotient rule. I'm not going to want to use the quotient rule on something that I could more easily just divide out by. I tell you, being a calculus lover as I am, this is my least favorite rule, okay? It's not my most hatiest rule, but it's maybe my least favorite of the rules just because there's so much stuff going on, and you got to make sure that you didn't drop anything. All right, but sometimes nothing's going to work except that quotient rule. I guess unless you combine it with some of the other rules, but I won't go into that. Let's see, we have a quotient here. All right, this is a quotient between two polynomials. This is actually a rational function. Keep in mind its domain. And there's no way for us to divide out, okay? Because you see, this is an x plus 17. If it was just an x, I could divide out. If it was just a 17, I could divide out, and that wouldn't even have any x's on the bottom, so that would be nice. When it's like that, I can't divide out. I have to use the quotient rule, and I want you to give me the derivative of this function in its simplified form using the quotient rule. The quotient rule will be given to you on a test or a quiz, so please practice now to see if you're ready with the rule right in front of you. Okay, I hope you're practicing. Let's see how this derivative came out. F prime, that's the top right there, goes to 2x. G is the x plus 17. Now I'm going to minus, and anytime I minus, I better have those parentheses in place. And likewise, I have to have these parentheses because you see there's some little bit of factoring that has to go on there. All right, let's see. What's the derivative of the denominator? X plus 17. Just 1, right, because that's the coefficient that's on this. There's a secret 1x whenever I see an x. And then we're going to leave the f alone, so we're going to get x squared plus 5, and that's going to be our entire top. And then on the bottom, x plus 17 quantity squared. Is it in its simplified form yet? Close, but no cigar. We have a little bit of combining of like terms to do. You can see that here, this top is 2x squared plus, what's 17 times 2? 34. Not as good with numbers as you thought, huh? All right, so the top there is 2x squared plus 34x, right? And then I have to minus, and now I'm going to factor through the minus sign. This is one of my most commonly seen mistakes, so please try to avoid making the mistake of forgetting to factor through the minus sign like so. So you see I actually have a minus 5, not a plus 5. And you see where I have some like terms, some combinable terms here? It's on the x squared coefficient where I have 2 x squareds, then I have a minus x squared, so really I just have 1 x squared. And I have 34 x's, and I have the number minus 5, and I'm going to divide that quantity just as I did before by x plus 17 squared. Now is it simplified? You better believe it is. It's as simple as it's going to get for me. Some people would say, well, don't I have to FOIL out the bottom? And I would say no. Actually, I kind of like it better without being FOILed out. If I ever have a polynomial that's already factored so I can see its roots, I kind of like that better. So this is a simplified form right here, and that would be the totally correct answer if I asked you for simplified form. All right. Now moving right along, I would like to check and see how much you guys remember from previous lectures. Let's say you're in some sort of class and you might have to take some sort of midterm. You're going to need to know a lot of stuff at once. So what is one of the other things that I taught you previously that's a very commonly asked question? That's going to be the equation of a tangent line. Okay, so let's take this same exact function right here, and I want you to, for part B, let's say this is just part A, find the derivative. Part B, form the equation of the tangent line to h of x at x is equal to, let's say 4. Okay, now the answer to a question of form the equation of the tangent line or find the equation of the tangent line, the answer is going to be in the form y equals mx plus b. Okay, that's the type of answer that you're going to box because it asks you for the actual equation of a line. Alright, so whatever you box here should be the equation of a line, and that's not to say that this function looks like this line. everywhere, but it is to say that if we really focus in here on the point x equals 4, if we zoom in on the function h of x and zoom in so we're super close to x equals 4, whatever answer we get here is going to be the line that this function basically looks like at that point. Okay? It turns out if you have a nicely behaved function and you zoom in very close on it, it always starts to look flat like a line. You know, back in the day they used to think the world was flat. I wonder why they would think that. Is it because the floor I'm standing on is flat? Something like that, right? When you're out in a big field and everything looks flat, you kind of think everything's flat. But the world's not flat, it's round. But when you zoom in closer and closer to the surface of the earth, where you're now standing on the ground at one spot, it looks flat. Same thing we have going on. That's a concept from calculus. Even as curvy as our function might actually be, if we zoom in close on just one point, it starts to look flat, which is to say straight, like a linear function, like a line. And that's the tangent line. This serves as a very nice linear approximation to our function. It's used all over the place in many applications, and so that's why we keep asking you, what's the equation of the tangent line? Alright, do you remember how to do it? Try to do it without any additional notes. I think you have enough information here. Here's the function. We don't need that one there. There's the original function. There's the statement of the derivative of the function. What else were we supposed to do so we can box an answer and get it right? Try to remember. Okay, so let's see. Our answer is going to be the equation of a line, and in the equation of the line there's two parameters or things that we need to find, and that's going to be what's the m and what's the b, right? So maybe you started on step 1. If you see my video for find the equation of a tangent line, step 1, find the m, okay? So we're going to find the m, the slope, and the slope of the tangent line is equal to the derivative, right? But I'm not going to take this whole equation and put it there. That's not the m. The m's a number. It's equal to the value of this when x equals 4, okay? So that means we have to evaluate h prime of 4. And I've done this, and I tried to double check myself this time. No typos, I hope. I got 147 over 441, and that actually simplifies down to 1/3. Okay, so if you plug in the number 4 on top and bottom, you should get a fraction that simplifies to the number 1/3, and so that means the m, the slope of the tangent line, is 1/3. But that's not the answer to find the equation of a tangent line. That would be the answer to what is the instantaneous rate of change of the function at the instant when x equals 4, or what is the slope of the tangent line, but not equation. Equation of the tangent line has the m in place right there. The answer is going to be with a 1/3 right here. And then it's also going to have a b. Alright, so that was step 2. And that's find the b. And how did we find the b? What other thing must we have to solve out for the b? That's going to be the value of the function at the point, right? Because see, this is an actual point on the function right here. X equals 4. H of x equals what? What height do we have for h of x? That's going to be h of 4. Okay, now notice the difference. Step 1, find the m. Plug in the value x equals 4 into h prime. Step 2, find the b. Plug in the value of x equals 4 into h of x. That's the difference. You wouldn't believe how many times I've seen students flip-flop those two things. So be very careful in your understanding of where you're supposed to plug in the 4. Okay, so if I plug in the 4 up there, I'm actually going to get 21 over 21, which is equal to 1. And getting h of 4 equals 1, which is to say that the point that lies on this function is a point 4, 1. Okay, that's what that actually means. Is if I pictured the function and I plugged in 4, I'd get out 1. That's a point on the line. Well, that's a point on the function h of x, and it also happens to be a point on the tangent line. And so we can use that to solve for b right here, because I know that 1 is equal to 1/3 times the x being 4 plus b, and now I can solve out for the b. See, I just have to move this 4/3 to that side over there, so b is equal to negative 1/3, and so my final answer to this question is going to be y equals 1/3 x minus 1/3. And those two number 1/3s came from different places. Actually, the m was plus 1/3, the b was minus 1/3. A little bit of a coincidence. Make sure you understand the full steps, and don't be surprised to see the question, find the equation of a tangent line on some sort of testing. Especially if you're taking it from me, but really, I couldn't see a calculus class without that type of question. So you probably will encounter it. I have a separate video on that called Finding the Equation of a Tangent Line if you're still having trouble. And today's topic was the quotient rule. For the product rule, I gave you a business application, total revenue being the product of price times number of items. The quotient rule actually has a great business application to go along with it too, and that's what we call the average cost. All right, average cost is going to be a little bit different than saying what is the average cost between this number and that number. So the average cost here is going to be defined as a new function that I form, c bar of x, okay? Now c of x should be familiar to you as the total cost function. C of x is the total cost of producing x items. The average cost c bar of x is actually that same total cost function. I'm not sure if you can see this, there might be some glare. Let me write it down here. The average cost function called c bar of x is equal to the total cost function divided by x, divided by the number of items. Okay, the average cost function conceptually is a per item cost, and you can see that if you start to analyze what kind of units we have on the function itself, c bar of x, because c of x, let's say that's the total cost, that's in dollars, x is in number of items. So what the output of the function c bar of x is conceptually the cost per item to produce when I'm at a production level of x items, okay? So like let's say it cost me $1,000 to produce 100 items, that's an average cost of $10 per item. Alright, now sometimes it's going to be helpful for us to look a little closer at this function, and we might want to even take its derivative, c bar prime of x, where we would want to take the derivative of the function, which is formed as a ratio or quotient of c of x over x. Okay, so we would want to do this. Let's get some numbers going to this example. Let's say our total cost function c of x is equal to 1,000 plus 2x. Okay, so let's say that we have a linear total cost where we have a fixed cost no matter what we do. We have to pay this $1,000 in fixed costs. It's kind of like renting the building. And then we have a variable cost of $2 an item, so we have to pay $2 for each additional item made. All right, now what's the average cost at a certain production level? It's actually not just 2, even though $2 per item is the variable cost, because the average cost also takes into consideration that if you only made one thing, it didn't just cost you $2 to make that one thing, did it? It cost you $1,002 for just that one thing. So if you have a production level of one item and you only made one item this month, that means that it cost you $1,002 per item. That doesn't sound that good, because you know that as you make more and more stuff, really it should be around $2 an item. That should be like your average cost, right? So let's form the average cost function here and see what it actually is. All right, so want c prime bar. You know what? My point is we're going to have to use a quotient rule, so yes, we will go ahead and use a quotient rule. But before we use a quotient rule, is this one where we could maybe just rewrite this? Simplify it, divide it out, write it in terms of fractional powers, and then take the derivative with the easier rules? This is one of those cases, so test your pre-calculus skills again and try to get the derivative c prime of x and try to get this without the quotient rule. And then on this board over here, I'll make some room for the quotient rule. Alright, if there's ever two ways, it would be great to try them both. So try to get the derivative of the average cost right now. C prime bar of x without the quotient rule. And then we're going to do it with the quotient rule, which is that h prime of x is f prime of x times g of x minus g prime of x, f of x, divided by g squared of x. Alright, did you go the easy way first? I really hope you did, because that would be nice if I saw that on a test. I'd rather just take c bar of x and rewrite it as 1000 over x plus 2x over x, which is 2. But I'm going to go even further than that. 1000 over x is actually the same thing as 1000x to the minus 1, and then plus 2. Alright, that's my easiest form. I don't have any x's on the bottom, so it doesn't appear to be a quotient. It just looks like a negative power. So luckily, I can just use a power rule, which is some of our easiest rules. So 1000 times the minus 1 minus 1000. And that's minus 1000x to the minus 2, right? Because it's minus 1. And then it went backwards by one more, minus 2. And what was the derivative of the 2? Oh, that derivative is just 0, right? Okay, so that's my answer right there. The derivative of all constants just goes to 0. So whatever I get with the quotient rule here, it should definitely look like that after simplification. Okay, so let's go on to use the quotient rule. And if you just went the easy way and you didn't try it this way yet, now's a good time. Now's a good time for me to do it. But before I do, how about you try it on your own? Pause the video. Okay, so let's see what you got from there. It's going to be f prime. Okay, so the top is f. What's the derivative of the top? Just 2. The 1000 goes away to 0. The 2x turns into a 2. G is the bottom, and that's just x. You know, even though 2 and x are such simple functions, I choose to put the parentheses around them just to keep in good form, because it's not going to hurt to have those parentheses around them, but it will hurt if you forget it in a place where you needed it. Okay? So you might want to practice that too. It's up to you. The derivative of the bottom is the number 1. Leaving the top alone gives us the 1000 plus 2x, and I'll divide all that by the bottom squared. Okay? So that one is just the x turns into an x squared, and now I'm going to combine like terms. So let's see what happens when I factor all that out. Notice how I have to watch out for that negative number getting multiplied through. 2x minus the 2x, hey, those cancel out. So I got just a negative 1000 over x squared. Is that the same thing I got before? Yeah, it's exactly the same thing. There's the negative 1000, and here the x to the positive 2 is on the bottom. Over there, the x is to the negative 2 on the top. So either way you slice it, this is what I would call the simplified form, okay? Either one of these things counts as the simplified form. Okay, so for my very last thing, just to keep testing your continuation of the other knowledge, what are the units on the derivative? Okay, so here's the derivative right there. The units on C bar of x, the average cost, has units of dollars per item. And that's because when we started the problem, we took the total cost, assuming that's in dollars, divided that by number of items here. That's the x unit is number of items. So the ratio or quotient for the average cost C bar has units of dollars per item. Okay, here's a question, maybe a little harder than you think. C bar prime of x, the derivative of the average cost, has units of what? Okay, this is a good question for you to try to answer right now. See if you can remember what I said before about how to form the units on a derivative. Did you get this one? You might think it's a little weird if you did, but the right answer is to take the y unit, which is dollars per item, and divide it by the x unit, which is number of items. Okay, so the actual answer on the units of the derivative of the average cost is dollars per item, or if you like, for those who've maybe seen physics or something like that, you know how we get the meters per second squared for acceleration, we can have dollars per item squared. If you want to write it like dollars per item squared, that's fine. Or I would also accept dollars per item per item. Okay, every time I ask you for the units on a derivative, I just want you to follow the same exact pattern. Take the y units, the units of the output of whatever you're deriving, in this case dollars per item, put it on the top. Then divide that by the x units. In this case, the x is in items. So you just follow that pattern. If you do that, you're not going to get it wrong. Okay, let's interpret that a little bit. C bar prime of x, that's the derivative. Okay, so the average cost, let's say, just for sake of example, let's say C bar prime of 100 is equal to, I don't know, minus 0.5. Let's just say that we took a value. Now, maybe that's not true for this right here. I'm just making up a number right here. But let's say that we have that the derivative of the average cost when we're at a production level of 100 items is negative 0.5. What is the interpretation of that? Interpret this. Okay, I'm going to want you to write a sentence that says, what does this value actually mean? And in order to help you figure out the interpretation, think about the units. And what I said before about interpreting the derivative in general is that the value, the number you get out of the derivative, is like if you move over 1 unit in the x, this is how much your y is going to change by. Okay, so use that with that over there. Alright, so I hope that you're taking the time to try to write something down. If I asked you a question like this, I would give you a bunch of different sentences and you could choose from one in multiple choice format. But as you move on to keep this knowledge with you forever, I think when you start to interpret derivatives, that's really what's going to lock you in to love calculus like I do. Okay, so let's say the interpretation of this is when making 100 items, remember, the interpretation is always going to start with the fact that the derivative is the instantaneous rate of change. So at the instant right now, where I'm at a production level of 100 items, if we increase production by 1 item, the y will go up by derivative value. And what's the y? The average cost will, in this case, it's negative, so it's not going to go up. It's going to go down. So go down by 50 cents. By half a dollar. Okay? So that's something similar to that is what I would expect to see in an interpretation sentence. At the very instant right now, when I'm making 100 items in my shop, if I chose to increase to make 101 items, the average cost, so the cost per item would go down by 50 cents, okay? And that's why it has the units of dollars per item, because it would go down by 50, sorry, I miswrote that. It would go down by 50 cents per item, right? Because the y value represents, C bar of x, represents the average cost or the cost per item. So the average cost will go down by 50 cents per item if I keep going. So it sounds like maybe I should keep producing more, because at least if I keep producing more right now, then my average cost per item would go down. If I ever took this derivative and saw a positive value, so that is to say if I start making more of them, the average cost to me per item will go up, that's maybe a sign that I should stop making more, okay? Which is also to say that whenever this derivative hits 0, might be an optimal place for me. We're going to find out more about that as we move along in the class.